Hello builders, my name's Mark and I make security and privacy easier to understand. Now when it comes to building out new technologies and new solutions, it's critical to make sure that security and privacy are a focus from day one. In this video, I'm reacting to an AWS cloud architecture by Lyft from September of 2016. Now we're going to look at the problem that they're solving through the lens of the AWS Well-Architected Framework. How did they approach the challenge at the time? What trade-offs did they make? And what could be changed now, given the latest features and functionality available in the AWS cloud? Now remember, we're not here to judge, just to learn and improve our own cloud skill set. So let's dive in. Okay, right out of the gate, I love the initial intro. They changed this a bunch over the years, and now it's a lot slicker, it's a lot quicker. But a good example of iterating, you gotta have something to intro the video. You can't just have two people talking right out of the gate, but that's just neither here nor there.
Welcome to This Is My Architecture. Simon from Amazon Web Services here, joined by Chris from Lyft. Welcome, Chris.
Great to be here.
We are going to be talking about some pretty cool stuff. We're talking microservices, we're talking discovery, but first,
Okay, so microservices and discovery. You got to remember back in 2016, there wasn't as many tools for microservice discovery. Kubernetes wasn't really a thing, if at all. It was still in its very, very early stages. So a lot of companies were dealing with this challenge of they had adopted the mindset of building out their service-oriented architecture in microservices, and they had to make sure that all these services could find each other. So let's see what Lyft has in store, what they built homegrown way back in the day.
let's talk about microservices and scale. You guys use microservices at Lyft.
Yeah.
How many? 1, 2, 3?
Yeah,
I'm going to assume that's a setup.
we started out with one, but today we're at about 150 across the company.
No.
Yeah, that was a setup.
And I'm guessing that, with all those microservices, you're moving really slowly, not much change.
Again, maybe just a tiny bit of a setup by AWS here, but it's good. It's serving the narrative, it's serving the purpose of kind of breaking down some early assumptions that people had back in the day.
That sort of stuff.
Yeah, quite the opposite. We've got about 30 different teams that are responsible for that set of 100 plus services, and we probably deploy a few hundred times a day.
Wow.
So 30 teams across 100 services, roughly 3 services per team. And the idea here, again, just to recap in a microservices architecture, is that you have a firm line, the API, between the various service teams so that I can be iterating at a different pace than you are. As long as that API is well managed and stable and well documented, I can make a ton of changes behind it to improve service delivery without impacting you.
A few hundred times a day. I know organizations that wish they could do that a year.
Yeah.
So it all sounds wonderful. That's why we go with microservices, to allow flexibility and agility. As we know, there's no architectural free lunch though.
Yep.
And one of the big challenges is service discovery.
So right out of the gate here, Simon has set it up and said, hey, you need to make trade-offs. There's no free lunch. And the biggest challenge, probably still to this day, is service discovery. How do you figure out how to communicate with these services effectively inside your organization? In the outside world, we interact with the API through its primary domain. You can do that internally, but again, it comes down to how are you making sure that you're getting the fastest response. Inside your application, you don't want the latency of all these different round trips and finding out who's up and running and where you can actually get your data back from the various microservices APIs.
You guys have a really interesting take architecturally on how you solve that. Take
Sure.
us through it.
Yeah, well, so at peak, our production infrastructure serves over 1 million requests per second.
Wow.
Okay, so this was 5 years ago, and they were doing 1 million requests per second in production. So we can see here they've got a couple setups. They've got a mobile handheld. They've got 2 different proxies with S1 and S2, which I assume is Service 1, Service 2. Then a DS box, which looks like an EC2 instance, and a Dynamo Datastore. So let's see as Lyft walks us through what the basic setup, what the basic flow is, maybe of a request. We'll see how they start this off.
So one of the things that's been really important is making sure we have the highest availability and reliability for both inter-service communication as well as end user kind of response latency. So
Okay, before he dives in, he just stated his #1 architectural priority, which is critical when you're applying the AWS Well-Architected Framework. The biggest thing they're worried about here is reliability. Totally makes sense. They have a service that has a real world component. I'm sitting on the curb connecting a ride, or I'm driving trying to find a rider. There can't be downtime here. That's not acceptable. So reliability is the number one pillar, which means they're going to sacrifice potentially on cost, on performance, on operational overhead or security in order to get that reliability. Now, obviously, they're not going to sacrifice everything. It's just a question of where are they making these trade-offs.
One of the things that we did is from the very beginning, the first server that our users will hit when they open up their phone to request a ride is this piece of infrastructure we built, which is a front proxy as well as an inter-service communication bus for all our different microservices. And what this service does, it maintains a local cache of every other service at Lyft and all the instances associated with it.
So the first thing any request hits, making these API requests is actually sort of a master index of everything that's going on. It's a routing proxy, but also it's a service health infrastructure, which is really interesting that they've got this double whammy, but it totally makes sense. First request comes in and it says, hey, I need the following. I need to make a transaction, or I need to leave a tip, or I need to request a ride. And then this proxy, it appears, is going to be able to not only facilitate that request, but make sure it's going through the most efficient route possible.
And that allows us to route that request to the lowest latency, healthiest service at any given time.
This is a proxy running on the EC2 instance that the service itself is running on, or a cluster of those in order scaling groups.
Exactly. Yep. And that.
Okay, so Simon just pointed out from AWS there that these are all running on EC2 instances or clusters of them, so auto-scaling groups of EC2 instances. That's probably something you would change today because there's a bunch of other options that are available, like containers in ECS, or maybe even going Lambda and using serverless designs. But 5 years ago, it made sense to build this out, especially when you're running the proxy in line with those things, because you want this to scale one-to-one. You don't want to have the proxy service having challenges of not being able to keep up and the actual microservices not being able to keep up.
Service basically out of band asynchronously will talk to a piece of infrastructure we built called the discovery service, which is its own cluster. And that discovery service maintains a list of all services at Lyft that it stores in DynamoDB. And when new instances come online, they'll register themselves with the discovery service. That'll get stored in Dynamo. And then any service that asks for the latest state of the world can get that, again, out of band asynchronously.
Okay, so this discovery service, the DS box up top, is creating and constantly updating a map of the infrastructure. So anything that spins up when a new EC2 instance spins up in an auto-scaling group, it doesn't just register with like a load balancer like it normally would. It actually registers with this discovery service saying, hi, I'm for the tipping app, tipping service, and here's my details. You can connect to me here. So this is sort of the single source of truth, is this discovery service. I shouldn't say single source of truth. It's the master source of truth, but they've already mentioned that the proxies handle some of this routing. So we'll see how they keep that up to date, because there could be a challenge of an instance is registered with a discovery service, but do the proxies know about it? Let's see if they address that.
From discovery service.
So how often would that proxy be hitting the discovery service to refresh itself?
It depends, but on average it's about once a minute.
Okay, so there you go. Every minute the proxy says, what's the state of the world? And it gets an update. So it's never that far behind, which would allow for a really high level of reliability, because even if it doesn't know about a new instance, it knows about the old one. So as long as they're healthy, it can keep routing there. It just hasn't routed to the new ones yet. So it's not bad to be behind, it'd be bad to be ahead. So if it knew about something that wasn't quite up to online and healthy yet. So that's interesting. Every minute those proxies are hitting it saying, what do I need to know about the world? And then they have a copy.
But the relationship, from what you're saying, is asynchronous with the discovery service. So how does the proxy work in relation to other services?
So the proxy basically will sit alongside every given service, and then when that request comes in, it'll look for basically if we have this request going from service 1 to service 2, it's actually going to go out through the proxy that sits alongside service 1, in through the proxy that sits alongside service 2, based.
Interesting. Okay, so the proxy is co-located with every single service has a copy of this proxy in it, which means that each service knows the state of the world, but the services don't communicate directly to each other. They communicate to the proxy and out. So you can think of the proxy like the load balancers. They've rolled their own, which totally makes sense because of this infrastructure, this sort of fabric they've got in place. But that also has a really interesting byproduct from a security perspective, is that all of the traffic from service 1 should be going only to the proxy and then out. it shouldn't be hitting the services directly. Same with all the incoming service communications into service 2 should be coming into that proxy. I really like that as a design. Not only is it giving you that reliability aspect, but it gives you a clear map of your infrastructure so you know where communication should be happening, and it gives you the ability to monitor, observe those, and potentially intercede if you need to.
The routing table that it gets from Discovery Service.
So each service is kind of independently aware of the other services around it.
Exactly.
Health checking, that sort of stuff?
Yeah, so each proxy does its own active health check-in. So what that means is in order for Service 1 to talk to this instance of Service 2, it must have learned about it from Discovery Service at some point, and it must have also passed active health checking from this instance of S1 to this instance of S2.
Okay, so they've got an extra level of reliability here. Is not only is the proxy checking the state of the infrastructure and looking at health checks, but they do independent or cross-service health checking as well. Is this healthy before it sends communications? And again, this comes back to their number one priority being reliability. They don't want to send a request that is not serviced. So they are taking an extra step. Instead of just one health check, it sounds like they have 2 health checks to your proxy as well as across services when they're calling in saying, hey, are you healthy first? You can facilitate that through a standardized API, basically saying service slash instance or health slash instance to give that ability to make it really straightforward. But they're doing a double check. They're saying, okay, this proxy, is this instance online? Yes. Instance, are you online? Yes. Okay, now we'll talk. Hit for performance because you're making double the calls and you have a huge amount of inter-service communication. However, you get that clarity. Now, this does also break that proxy-to-proxy communication thing because it sounds like they're going directly in, but I believe they route that health check through the proxy as well. So it doesn't really break that model. That model's still in place, that route is going through the proxy, but the proxy is the ability to health check individual nodes and reply that back to the other service. It's really clever. Again, performance hit is double because you're making 2 requests before you're actually sending your valid communication request. You're making these 2 health check requests, but it falls in line with their requirement for reliability above all else.
And I say learned about it at some point because we've designed this infrastructure to be so resilient that both the data store associated with Discovery Service DynamoDB could entirely disappear, which we
Not that that's ever going to happen.
Exactly. Or the Discovery Server itself could totally go offline. And what happens is every instance will maintain the last known state of the infrastructure and use both that set of instances as well as the instances that it knows are healthy from active health checking to route those requests.
Wow. Okay. So again, reliability is the number one thing and they mean it. So what they've said is that the DynamoDB backend of the Discovery Service could go away and Discovery Service has a localized cache of it on each instance and still service the requests, or the entire Discovery Service itself could go away and all of the proxies have that map and they do that active health checking so that the infrastructure would still operate even if the Discovery Service, which is the number one service within their infrastructure, even if it went offline, they'd still be okay. That is a very, very resilient service. But again, it ties to a real world need. Most of us aren't in a scenario where we're designing something that has a physical component. Lyft is. It's obvious in their design here. They've really taken care to make sure that nothing is going to take this thing offline.
So if this disappears for a second, it's fine. Disappears for 10 minutes, it's fine. Even a few hours, we'll continue to serve traffic reliably.
Right.
Yep.
So let's dive a little bit more deeply into the Discovery Service. How's it built? How's it operate?
Yeah, so Discovery Service is built in Python, and it's
Okay, so they built it in Python. You may be thinking, oh, that's not nearly performant enough. Given the level of reliability, and given all that is essentially adding, it's just a front end for Dynamo. It's just storing keys and values. Service 1 has the following instances that are active. They were last checked. I'm sure it's got a very simple schema, and it makes sense that Python, they're optimizing for developer experience here. They're not, they probably have a team that's familiar with Python, so they built it out in that because performance is absolutely critical here. Every updates are happening every minute. They're receiving new requests constantly as things go in. Python can more than keep up with this, so they're optimizing for a different factor, which is let's make our developers happy. Let's make this code easy to understand.
One of our higher volume services at Lyft, not the highest, but it's something that we definitely have in an autoscale group, so it can ramp up as the individual number of service instances also scales.
And DynamoDB, why the choice of that as the data store?
Yeah, DynamoDB is great because it gets out of the way in terms.
And that's critical for Dynamo. It really does get out of the way. It's a simple key value store. Back then you had to actually assign provision capacity, but now you have auto scaling. And so you don't even have to worry about that anymore. But basically they had to say at max, we'll do this many reads or this many writes and pre-assign that and pay a certain amount for that capacity. But given the criticality of this service, it's a trivial cost. But the idea here is it's got almost no operational overhead in Dynamo, yet you get a massive amount of reliability. It's really a win across almost all 5 pillars for the AWS Well-Architected Framework.
Being a highly available, reliable production data store, there are only 2 ways that you can scale it. Read IOPS or write IOPS, and not having to worry about chunk migrations or dealing.
So he's talking about that read and write capacity. Again, that's gone and we're now into auto scaling, but he's also comparing it to other database stores where you don't have to worry about sharding the database, you don't have to worry about the scale, things like that. And I'm sure at some point the global tables would actually be an advantage for them for reliability alone. It doesn't sound like the discovery service would need that big of a data store, but just the basic hands-off nature of Dynamo is really paying off.
With the on-call rotation for that data store is just makes this whole service
so
something we don't have to spend much time thinking about.
Which is interesting because it is so critical, and it's kind of like the magic that strings all these things together.
Yeah, I think the traditional approach to service discovery is a strongly consistent system, and we've taken an eventually consistent approach to service discovery.
So there, when he's talking about an eventually consistent approach, that's really critical, is because they've got all these multiple copies. It's okay for a copy to be out of date because it's doing that extra health checking. But also, if it just doesn't know about extra capacity, that's okay. It can learn about it in the future because it's still got something to serve with. Now, in the event of a disaster recovery where there's no available capacity, that might be a problem. But it sounds like this is so reliable and they've got so much information about the health of their infrastructure. That's a really rare case. And again, reliability is a huge concern of theirs. So I'm sure they've got an aspect of this design that we don't see that covers that off.
It's just eliminated so many headaches from our microservice architecture.
That's brilliant. So you've used auto scaling for resiliency. You've got local discovery of services. You've built a robust discovery service, I should say, that's not going to go anywhere unless something really, really bad happens. You've got a durable store of state.
Yep. And the one other great thing that this piece of infrastructure provides, given it's located on both the client and server end of each call, is an incredible insight into the performance, success rate, latency of every single RPC that we make at Lyft.
So you're getting lots of metadata that you can action.
Definitely.
Okay, so this design, really impressive. They stated their architectural need right out of the gate. They said reliability is number one. They built this proxy system that sits in front of every service to handle all the communications. And that proxy service allows other microservices to health check the internal state of various instances, which may break the microservices model a tiny bit, but in a way that totally makes sense and is consistent with their goal of reliability. Now, this was 5 years ago. This was in 2016. So they are building this around EC2 instances, and that was probably what I would change. I'd still stay with for the discovery service, and the overall design is brilliant. I would still stick with DynamoDB for the discovery service data store. It's only gotten better, and it was already great. So that auto scaling has really made it easy to solve this need. The discovery service itself, I'd probably switch to Lambda because of what it's doing. Go to Lambda at scale as long as the capacity for the request was there. That makes sense. For the individual microservices, you might want to think about not just the proxies, but the API gateway. Now, the proxies, actually, let me reconsider that. The proxies, I would probably either keep them as a container or as an EC2 instance, but behind those, now you have the flexibility of using Lambda, using containers, using instances, whatever makes most sense for that particular microservices design. But if you keep those proxies running in EC2 instances, yes, it costs a little bit more, but you're really simplifying that load balancer in front, because the load balancer can't do what you want it to do. It's going to balance the load across those EC2 instances, but it's not giving you that complete replica of your infrastructure. They're really, the proxy service is almost like a copy of every single load balancer within the system. So I would stick probably with EC2 instances running those proxy services, because you get that higher level of network assurance, and you can customize the instance type to the network capacity that you need to handle for each service. And then behind those proxies, I would start looking more and more to serverless. I would start looking more and more to containers. But overall, this design, I love it. They stated very clearly what they wanted, which was reliability, and they have that in spades. They've got a number of scenarios where if things go down, they're still reliable. He said it directly. That discovery service can go down for a couple hours and they're still fine, and they still operate. It may not be perfect efficiency, it may not be as performant as it normally is, but it's still working, and that's critical when you have a service that has a real world need. Overall, this architecture is held up. There's some optimizations that you would do, which totally makes sense over time. But yeah, so overall, this architecture is absolutely held up. It is great. A few tweaks here and there to take advantage of some new features in the AWS cloud, but an impressive design that seems to have withstood the test of time, which is an amazing thing when it comes to technology, especially when it comes to cloud technology. And they balanced really well for resiliency, and had some interesting optimizations around security with that core restricted network flow, which is really impressive. Job well done, Lyft, and I'm sure it's even more impressive today. And we'll see you builders in the next video.